Hey guys, in this video we'll be going over problem 1 from the practice topic 9 problems. We're given a differential equation, which again just means there's a derivative involved in there, and we're trying to solve it, meaning we're trying to integrate. The methods we know for doing this are separation of variables. If it's homogeneous, we can do the substitution v equals y over x, and if it's not homogeneous, and then you can't separate the variables, we can do the integrating factor method, where you let this integrating factor be e to the px, and it has to be in a certain form for that to happen, right? So we want to look at this and be like, try to ask ourselves first, can we separate these variables easily, right? Can we get all the y's on one side, all the x's on one side? You might do some algebra, usually involves some sort of factoring. What I'm going to try first is go ahead and just move the 2xy over to the other side. So we'd have this. Then we try to think, is there any way for me to get y by itself? I can see this is a difference of squares, so maybe y minus 1, y, y minus 1 times y plus 1. Oh, there's like a dead spot on my screen or something. Let's see if it works up here. Yeah, I guess there's a dead spot on my screen. Over 2xy. Sorry, not 1. This should be x. But even that doesn't seem like it's working very well. So what I want to try to do is, let's look at homogeneous first. The reason I'm not saying integrating factor method is integrating factor method, usually there's not anything next to the dy dx. So I'd have to figure out a way to rewrite this so that there would be a function of x next to a y, and then another function of x all by itself, and that wouldn't be able to be there. So let's see if we can write it, meaning I want a function of y over x. So we could try dividing everything by x squared, or multiplying everything by 1 over x squared on the right hand side. So that would be y squared over x squared minus x squared over x squared over 2xy over x squared. If you simplify this, you're going to get y over x quantity squared. This just turns into 1. Down here you get 2y over x, right? And once you do that, you can then say, okay, I can do a substitution now, right? I'm going to let v equal y over x, right? Therefore, y is v times x, right? So I could then rewrite this equation as dy dx equals v squared minus 1 over 2v. And then we have this dy dx, and if this is the case, we want it in terms of v, so we're going to take the derivative of this, right? Derivative of y is dy dx. Derivative of the left-hand side requires product rule, right? It's going to be v times derivative of x is just 1, plus x times derivative of v, which is x times dv dx, right? So now I know dy dx is this thing, so I'm going to replace dy dx over here with this thing. And I get this. We can try subtracting v on both sides. We get x dv dx equals, if I subtract v, I need a common denominator, so I'm going to multiply top and bottom by 2v. This would be negative 2v squared. So now I have negative v squared minus 1 over 2v. Remember, whatever variable is in the numerator, that's the variable that's going to need to be on this side. So I need all my v's over here. I can multiply by the reciprocal on both sides, and I'd get 2v over negative v squared minus 1 dv dx equals 1 over x, right? We also divide by x on both sides. And then when we integrate, it's going to become 2v. Maybe it's easier if we just put this negative 1 on the outside. And maybe you can see what that is. dv equals integral 1 over x dx. The right-hand side is easy. That's just natural log x plus c. The left-hand side, I don't know if you see it, but I'll do it over here. You could do a u substitution of v squared plus 1. Therefore, du is 2v dv. Therefore, dv is du over 2v. So you come back over here and you say, okay, this is 2v negative. This whole thing is u now. dv is du over 2v, right? So cancel, cancel. You're left with the integral of negative 1 over u du, which is natural log u, but remember u was v squared plus 1. So we get that. Right, so then, I don't know what you want to do with this negative. Kind of depends how you want to look at it. We could use the property of natural log, put it up here. We could divide both sides by -1. I don't know what's going to be the easiest here. Let's say we, I don't know, let's just, let's divide both sides by -1. So then this side is going to be negative ln x. We could then try to solve for this by raising each side to the e power. These would cancel. You get v squared plus 1 equals, or this time we're going to have to move that e to the power. So it's going to be natural log like that. And the e to the ln cancels. You're left with x to the -1. Nope, sorry. Let me slow down here. We have e to the natural log x to the -1 plus c. We're going to use the property of exponents, or if I see an addition up here, it becomes a multiplication down here. These ones will cancel, and then we're going to also let e to the c equal a. We're just making that up. A equals, no, a times x to the -1, or 1 over x. So then we have a over x here. Right, and from there, we can then substitute back in what we had, which was v equals y over x from the beginning. Right, so this is y over x squared plus 1 equals a over x. So this is y squared over x squared plus 1 equals a over x squared. Let's try to get rid of the x squared. So this means we multiply everything by x squared. Sorry, this is not x squared, this is x. And you get y squared plus x squared equals ax. So y squared equals negative x squared plus ax. I don't remember if they gave us an initial condition. Oh, we're trying to show it like this: x squared plus y squared equals cx. So actually, just stop right here. And instead of calling a c, let's c equal a. So there you go, we're there. And that's the first part. Okay, for part B, they want us to prove that there are two horizontal tangent lines to the general solution curve and state their equations in terms of C. Remember, horizontal tangent lines mean that the slope is 0, and so in this case our slope is given by dy dx is 0, and this is to the general solution, so we don't, we already have the derivative, right? Remember in the beginning we said the derivative of this function, if you look at your original equation up there, was y squared minus x squared over 2xy, and so we're trying to show when will this be equal, when will our slope be equal to 0, and so we could set it equal to 0. All that really matters is the numerator, and so we get y squared equals, when y squared equals x squared, if you take the square root of both sides, you get when y equals plus or minus x, right? So we will have horizontal tangents when y equals plus or minus x. That is not our solution, obviously, right? So we need to go back to our general solution, which is y squared plus x squared. There's my dead spot again. Y squared plus x squared. Let's try y squared plus x squared equals a.
You left your room open again. The cat's gonna pee on your clothes. Go close it.
We know y equals plus or minus x. We'll do one at a time. So in the first one, we'll do x squared plus x squared equals ax. Therefore, 2x squared equals ax. We're trying to solve for, what are we trying to do? We're trying to prove that there are two horizontal tangents to this, state their equations in terms of c. So we're trying to find out what is the equation for this in terms of c. So then we could try to solve this equation for x, right? And maybe I should write this as a c since they want it to be c. To solve an equation like this, we should set it equal to 0 and try to factor out. So you'd have x, and you'd have x minus c, 2x minus c. And so one of them is when x equals 0, the other one when is 2x minus c equals 0, or when x equals c over 2. And then let's think. So that's where this occurs, and then we would want to find out the prove that there are two horizontal tangents to the general solution curve and state their equation. So we need to state the equation of the tangent line, right? So so we know that, hold on, let me think about this. Okay, so what we found is the x-coordinate of the horizontal tangents. To find the y-coordinate, we could come back over here. And so the y-coordinate would be at positive c over 2 and negative c over 2. What we might think is, okay, it wants the equation of the tangent line, which is typically this, right? So we might write, okay, y minus c over 2 equals our slope. What was our slope? Well, it's a horizontal tangent line, so the slope is 0. And then you can see, oh, well, that piece doesn't matter. And so the actual equation is just y equals c over 2. And if you do the same thing with this one, you would get y equals negative c over 2, right? And so these end up being all you need as far as you need to go, because they are horizontal tangent lines. They'll just be y equals and there won't be any x, right? So that's the two that we get.